For the last century, theoretical physics has been defined by a persistent dialectic between two opposing conceptions of reality, the continuous and the discrete. General relativity models gravity as the curvature of a smooth, continuous spacetime manifold. Conversely, within quantum field theory, it characterizes matter and forces as discrete, quantized excitations of abstract energetic fields. Standard analytical solvers frequently classify the resulting dimensional mismatches as computational failures. When these two frameworks interact, the math often yields uncomputable phase spaces and division by zero errors. The theory of infinity, or TOI, treats this continuous discrete dichotomy not as a mathematical failure, but as a structured operational boundary. Within this framework, ordered information can be lawfully transported across this divide. To manage this transport, the mathematics must navigate a not-infinity boundary event. A not-infinity boundary is the precise event horizon where unstructured potentiality is accessed and configured into structured mathematical information. Analyzing this interaction requires shifting away from post-empirical higher-dimensional models. We must instead map exactly how mathematical data survives crossing this infinite boundary by auditing its topological stability. The mechanical tool designed for this transport is the Master Orthogonal Filter Law. It serves as the primary algebraic engine for moving data across the not-infinity boundary. Its core function systematically collapses complex, two-dimensional continuous spatial geometries into pristine, one-dimensional discrete mathematical payloads. The central filter acts as an orthogonal identity plane, filtering out unbounded background noise to protect core data and yield a perfectly sealed scalar output. Following the comprehensive canon revision of 2026, researchers integrated a new suite of exact integral families into the TOI architecture to test the architectural integrity of this dimensional filter. This process establishes that infinite spatial domains can be mathematically sealed. It allows researchers to evaluate continuous wave geometries as discrete algebraic outputs without structural decay. This equation represents the Master Orthogonal Filter Law, operating over a continuous potential space. It relies on a double integral structure with distinct upper bounds, a finite target on the y-axis and an infinite domain on the x-axis. The operational challenge is one of entanglement. The system must calculate the target geometric function on the y-axis while it is mathematically bound to an infinite inverse power decay field on the x-axis. To isolate the target, the solver applies Fubini-Tonelli constraints. These are conditions that allow for the reordering of integration. Because the domain is finitely bounded, these constraints allow the continuous double integral to separate into two completely independent one-dimensional integrals. The y-axis integral evaluates via standard continuous calculus. This leaves the x-axis to bear the entire burden of the infinite boundary interaction. This separation is the critical first step in the protocol. It detaches the physical target from the infinite potential background without causing a computational crash. This equation isolates the infinite x-axis integral, displaying variables a and b. The system seals this domain by locking both to the golden ratio, whose unique recursive property triggers a mathematical self-annihilation. This collapses the unbounded integration down to a perfect absolute one. The framework defines this unblemished scalar output as the golden unit seal. This operation creates a pristine continuous vacuum. By limiting the infinite orthogonal integration to exactly 1, macroscopic geometries can pass through the matrix while remaining perfectly preserved in their original magnitude. Researchers then shifted the evaluation to the complex plane, injecting imaginary arguments into the integrals to test the framework's ability to handle phase inflections. Phase inflections are points where a mathematical construction crosses a branch cut or sign constraint, requiring the insertion of complex phase to prevent context collapse. These complex tests use a tripartite morphology taxonomy. This system classifies the math into 3 parts: the worm, which is the underlying manifold substrate, the worm, the active mathematical operator traversing it, and the y-arm, the absolute geometric invariant being transported. The real channel's output, pi/2, is the y-arm, the sealed invariant representing the perfect quarter-turn closure of the base geometry. Conversely, the kinetic friction incurred by the worm operator traversing the discrete manifold is banished into the latent imaginary channel. This extraction proves the framework can segregate absolute physical form from the necessary friction of mathematical transport without contaminating the core data. This table displays the epistemological status scorecard used to audit claims through the trimodal invariance rule. This rule requires that any stable invariant demonstrate structural coherence across three modes: geometry, algebra, and discrete logic. The highest status on this scorecard is sealed exactness. A claim reaches this level only if it contains zero calculated residuals and is independent of finite numerical approximation. We can contrast this with the Pythagorean sentinel and the rational 2/5 echo. These artifacts produce outputs that appear mathematically adjacent to fundamental constants, but are actually finite numerical approximations. The Pythagorean calculation mimics the true vacuum partition constant, but misses the target by a measurable residual, meaning it fails the test for exactness. To maintain rigor, the framework enforces a transform penalty. This prevents researchers from using arbitrary multi-step algebraic manipulations to force a false numerical alignment between continuous and discrete forms. Within this system, these near misses are defined as dimensional exhaust. They act as diagnostic guardrails, proving that modal content leaked during transit and absolute exactness was not achieved. This leads to a mechanical question. When a fractional residual is generated as dimensional exhaust, is that mathematical data permanently lost? The conservation of modality law states that this information is never destroyed. The data is carried inside a charm monad, a portable structure that packages a target invariant, its residuals, and its exact modality binding. As data crosses the infinite boundary, kinetic friction is safely siphoned into a latent tension modality by a cybernetic valve. The J-GLOW global invariant acts as a final check, rigidly conserving the sum of the manifest output and latent exhaust across the transport chain. This cybernetic ledger allows researchers to track exact geometries across not-infinity event horizons, accounting for every fraction of topological overlap during the transition. The execution of the Master Orthogonal Filter successfully demonstrates that infinite continuous variables can be packaged into discrete algebraic bounds. This verification supports a core philosophical mandate. The absolute architecture of reality is not constructed upon finite arithmetic approximations. Instead, those finite numerical readouts are merely positive correlation signatures, the dimensional exhaust left behind by the true underlying mathematical invariants as they traverse the discrete matrix. The theory of infinity and its cybernetic J-series regulations provide a structured protocol for auditing these modal transitions. By treating infinity not as a paradox, but as an operational boundary, we can finally map the exact borders of mathematical and physical emergence.